Hello, this is Mr. Combs, and let's talk more about simplifying radical expressions. So we talked about the fact that the nth root of x to the n is just x, but actually that depends on whether n is even or odd. So if n, or the index, and the exponent is an even number, then we have to have absolute value bars around the x. And this just gives us a way to ensure that we always get a positive result when taking an even root. Because remember, we cannot have a negative number under an even radical, or if we do, that is not a real number. We'll talk more about that in a moment. But if the index and the exponent is odd, if n is odd, then we can have just x without the absolute value bar. So if x is negative, then it remains negative. So to make this a little bit clearer, let's look at a couple of examples. Let's actually look at the examples that I have here. If I have the square root, and remember, if we do not have an index here, then we're going to assume that the index is 2. We're going to assume that is a square root. So if I have the square root of -7 squared, well, you might think that, based on our rule earlier, you might think that the answer to that is -7. But remember, the square root or an even root is never negative. So this gives us, the rule that we just talked about gives us a way to say this is in fact a +7. Because in fact, n is even, so the exponent and the index are both 2, right? So really what I have is the absolute value of -7. So that becomes 7. So that in fact is positive. Okay? Over here though, n is odd. So I have an exponent of 3 and an index of 3. So that means that I can just take x itself. So this is just -8. Okay? You shouldn't have too many problems where this kind of thing factors, but if you do, now you know how to handle it. So what if I have something like the fourth root, let's see, the fourth root of x to the fourth? Well, if I wanted to simplify that, remember that n is even in this case, so I would have to write the absolute value of x. And since I don't know what x is, I'm just going to leave that way. But let's say I had the fifth root, of x to the fifth. Well, in that case, I can just write x, because that's an odd index and exponent, so I don't have to worry about taking the absolute value. Okay? Okay, when we start to simplify radical expressions, we need to take into consideration perfect powers, whether we have numbers or variable expressions. So I have here that a perfect nth power number is a number that has an integer root. And to find these, we're usually going to just use a chart, a list of perfect powers, or use your calculator. Excuse me. So let's say I have a situation like this, where I have the square root of 36. Well, I know that 36, from my knowledge of multiplication, or I can look at a chart, or I can use the calculator, I know that 36 is a perfect square. So 36 is a perfect square because it has an integer square root. If I take 6 and 6 and multiply those two together, or multiply 6 by itself, I get 36. So the square root of that is 6. So 36 is the perfect square. You can have a perfect cube, you can have a perfect fourth, you can have a perfect fifth, and so on. So Another example might be, let's say I wanted to take the fifth root of 32. Well, I happen to know that if I take 2 to the fifth, I'm going to write that up here, and I multiply 2 by itself 5 times, I'm going to get 32. So 32 is a perfect fifth because the fifth root of 32 is 2. Okay? So 32 is a perfect fifth. 36 is a perfect square. A number like 8, for example, since the cube of 2 is 8, 8 is a perfect cube, and the cube root of that is 2. All right? So if I'm dealing with a variable expression, it's a little bit different. If we're thinking about a variable expression, then a perfect power variable expression has an exponent that is evenly divisible by the power. Okay? So if I'm thinking of perfect squares, a perfect square variable expression might be x to the 8th, because 8 is divisible by 2. Okay? So that's a perfect square. PRF, perfect square. If I'm dealing with, maybe I have x to the 7th, then that is a perfect 7th. Okay? Because 7 is divisible by 7. So this is a perfect 7th. Okay? Now the way that I find the root of a perfect power variable expression is I just divide the exponent by the index. So let's say that I have the cube root of x to the 12th, and I want to actually simplify that. Okay? Basically all I'm going to do is I'm going to take the, having trouble writing my equal sign here, I'm going to take the exponent 12 and divide it by 3, the index. So 12 divided by 3 is 4, so this is, the root of this is x to the 4th. Okay? So this helps us to simplify radicals like this. Okay, here we have several radicals. I want to simplify these. So remember that when I'm dealing with the numbers or the coefficients, I'm going to use my knowledge of squares, or squares and cubes and fourths and so on, or I'm going to use a chart or use my calculator. Okay? So here, in this first one, we have 32 x to the 5th, y to the 15th. So I think to myself, is 32 a perfect fifth? Well, we said before it was. The fifth root of 32 we said was 2, because 2 to the 5th power is 32. Now, is x to the 5th a perfect fifth? Yes, it is, because 5, the exponent, is divisible by the index or the power, or the root, 5. So that is a perfect fifth. Y to the 15th is also a perfect fifth because 15 is divisible by 5. So how do I do this? I just simply divide. So x to the 5th, 5 divided by 5 is 1. So the fifth root of x to the 5th is just x. And then for 15, 15 divided by 5 is 3. So the fifth root of y to the 15th is just y to the 3rd. So this is 2x y to the 3rd. Okay, let's try another one. What is the cube root of 8? Well, I know that 2 cubed is 8. So the cube root of 8 is 2. And all I have to do here is just divide 6 and 9 by 3 to get the cube root of those variable expressions. So 6 divided by 3 is 2, so that's x squared, or x to the second. And 9 divided by 3 is 3, so that's y to the third, or y cubed. And that is that radical simplified. Alright, well, let's take a look at the next one. I have the square root. Remember, if there's no index, we assume it's a square root. So I have 4. The square root of 4 I know is 2. And I have x to the 8th, y to the 10th, z to the 16th. So all I have to do is divide each of those by 2. So x to the 8th, 8 divided by 2 is 4, so that becomes x to the 4th. Y to the 10 divided by 2 is 5, so y to the 5th. And z to the 16 divided by 2 is 8, so z to the 8th. This is for x to the 8th, y to the 10th, and z to the 16th. When you find the square root of that, you get 2x to the 4th, y to the 5th, z to the 8th. So, getting the hang of it now, I think it's once you understand what's going on, and if you keep a list of at least perfect squares up to 100, perfect cubes up to 100, perfect fourths, if you keep that, or if you keep your calculator handy, it's not so bad. So 64, what is the square root of 64? Well, what times what is 64? 8, right? So the square root of 64 is 8. And to find the square root of x squared, all I do is I say 2 divided by the index, which is 2. So 2 divided by 2 is 1, so I really have x to the first, or just x. But now hold up, this was one of those situations where I have an even index and an even exponent. So really what I should probably represent this 8x as the absolute value of x, just to make sure, okay? Just to make sure that that x is always going to be positive, end up being positive. But here, the cube root of negative 64, well, if I take negative 4, right? 4 times 4 is 16. 16 times 4 is 64. Yeah, so if I take negative 4 and I multiply that by itself 3 times, I get negative 64. So the cube root of negative 64 is going to be negative 4. Okay? And then if I take 3 and divide it by 3, I'm going to get 1. So in this case, I'm going to have negative 4x. So the cube root of negative 64x cubed is negative 4x. That was an odd index and an odd exponent, so I don't have to worry about putting absolute value bars around x. And you know, sometimes you'll actually have a textbook that says, let's assume all variables are positive, so you may not actually get a textbook, or you may not, when you do your homework, be required to put those absolute value bars around x. So you may be able to just write 8x, and that might be okay too, okay? But I would always start out writing the absolute value bars just to make sure that we end up with a positive number, unless you have a direction at the beginning of your homework that says, let's assume everything's positive, or all variables are positive, or something like that. So in this last case here, we have the fifth root. I don't have a number there, so I don't have to worry about taking the fifth root of anything number-wise. I just have to worry about these two variables. So what I need to do to find the root of a variable expression is divide the exponent by the index. So 10 divided by 5 is 2, so this is going to end up being x squared. And 30 divided by 5 is 6, so that's going to be y to the 6th. And we don't have to worry about here putting absolute value bars because x squared, when you square a number, it's always going to be positive. The result will always be positive. When you raise something to the 6th power, or in fact any even power, the result is always going to be positive. So you don't have to worry about putting absolute value bars there because those will be positive anyway. So these were all expressions that happen to be perfect powers. Okay, we had a perfect cube, we had a couple perfect fifths, we had some perfect squares, another perfect cube. But what if you have a situation where your radicand, or the expression under the radical symbol, is not perfect? It's not a perfect cube or a perfect square or a perfect fourth. Well, you can still simplify those as well, and I'm going to show you how to do that next. Okay, let's take a look at these square roots, and let's simplify those. Okay, now you could always use a calculator when you have just numbers. Like I can find the square root of 72 on a calculator. The problem with that is that it will give me a decimal, okay, or a decimal approximation. Anytime you take the square root of a number and you get a decimal by using a calculator, that's called an approximate answer. Sometimes we need an approximate answer, like if we're doing measurements. But sometimes in algebra, we need an exact answer. An exact answer will be one that doesn't have a decimal approximation, but it uses a square root symbol, okay? So an expression is simplified and you have an exact answer when underneath the radical you have the number underneath the radical, excuse me, has no perfect factors, okay? So let's look at the square root of 72, okay? If I can take the square root of 72, if 72 is a perfect square, then I just find that square root, okay? In this case, it's not. So what I'm going to do is I'm going to break 72 up into two different radical expressions. Under the first radical symbol, I'm going to put the perfect factors of 72, okay? So everything I can take the square root of, okay? And then under the second radical symbol, what I'm going to do is I'm going to write what's left, okay? Now, you need to be careful here because we want to make sure that we take the largest factor of 72 that is a perfect square. So I'm thinking to myself, well, how can I break up 72? Well, I can break it up into 8 and 9, right? 8 times 9 is 72. 9 is certainly a perfect square factor, but there's also a perfect square factor in 8. 4, right? So there's something larger. So if I look in a chart of perfect squares, I notice that 36 is a perfect square. It's 6 times 6. And 36 is also a factor of 72. So what I can do is I can break up 72 into 36 times 2. Okay? 36 is the perfect square part of 72. It's the perfect square factor. And then 2 is just what's left over. So when I simplify this, I always take the square root or take the root of the perfect part and then leave the what's left over part alone. So 72 is going to be, square root of 72, excuse me, will be, square root of 36 is 6. And then I'm going to have the square root of 2 left over. So 6, the square root of 2. That's the square root of 72 simplified. Now, let's look at the square root of negative 35. Well, I have an even index, 2. There's no index there, so we assume it's 2. And I have a negative number. Remember, that can't happen. You cannot have a negative radicand when you have an even index. So basically, if I see this, if I see a negative number here and the index is even, the index is 2, 4, 6, so on, I'm just going to have to say that in this case, this is not a real number. Now, in chapters later on, we may be able to do something more with that. But for now, it's just not a real number. Okay? Now, the same thing isn't true for the cube root. Remember, we can have negative cubes. So I'm going to try to break the cube root of 24 up into a perfect square part, or a perfect cube part, excuse me. Watch out for that, because, we'll most often deal with squares, but sometimes we'll have cubes and fifths, so you got to worry about that, or keep watch. So a perfect cube part of negative 24 and a what's left over part. Let's see. Well, I know that 8 times 3 is 24, right? And negative 8, or 8, happens to be a perfect cube. 8 is 2 cubed. So what I'm going to do is I'm going to write a negative 8 in my perfect part. And then what's left over after I take 24 and divide it by 8? Well, negative 24 divided by negative 8 is 3. So now, to simplify, I simply take the cube root of negative 8, that's negative 2, and then I have the cube root of 3 left over. And that is that expression simplified. Okay, let's look at 700. 700, what can I break? 700 is not a perfect square itself. So it's the square root of 700. What can I break 700 up into? What is a perfect square factor of 700? Well, if you think about it, 700 is 7 times 100, right? 100 is a perfect square. What is 100, the square root of 100? It's 10, right? So 100 times 7 is 700. So the square root of 100 is 10. And then what I have left over? The square root of 7. So this one is 10, the square root of 7. Okay, let's look at the square root of 98t cubed. 98 is not a perfect square, so I'm going to break this up into a perfect square part and a what's left over part. Well, 98 is 2 times 49. 49, I know, happens to be a perfect square. The square root of 49 is 7. So 98 divided by 49 is 2, so I'm going to put 2 over here. Now when you look at each of these, this expression and this expression, when you're done breaking everything up, you should be able to multiply those two things together and get the original radicand. Okay? Now this is the first time that we've had a variable. Remember, we said that a variable expression is a perfect power. In this case, it would be a perfect square if the exponent is divisible by 2. Well, in this case, 3 is not divisible by 2. But we can actually break t cubed, or t to the third power, up into two different expressions, one that is divisible by 2 and one that's whatever's left over. We can break t cubed up into t squared times t. Right? Remember that you are adding exponents when you're multiplying variables. So t squared times t is t to the second, 1, 2, times t to the first, 1, so 2 plus 1 is 3. Alright, so what you're looking for when you're breaking up a variable is the largest number less than your exponent that is divisible by the index. Okay? In this case, it happened to be 2. So now on this side, I'm going to take the square root. So the square root of 49 is 7. And the square root of t squared is 2 divided by 2 is 1. So that's just t. And then here I'm going to have 2t, the square root of that, left over. So this is my simplified form there. 7t square root of 2t. Let's look at square root of 180 x to the 5th y to the 3rd. So 180 is not a perfect square. So I'm going to break it up into 2 radical expressions. Let's see, 180. Well, 180 is... I know 9 will go into 180. Is there something larger? What about 36? What is 180 divided by 36? Right, it's 5, right? So 36 and 5 is what's left over. So 36 is the perfect square part. Square root of 36 is 6. And then I have 5 left over. Okay, let's look at the variables. X to the 5th. Well, 5 is not divisible by 2. So I'm going to need to break x to the 5th up. I can break x to the 5th up into x to the 4th and just x, right? Okay, and now let's look at y to the 3rd. Well, 3 is not divisible by 2, but I can break y to the 3rd up into y squared and y. Alright, now I have my perfect square part. I'm just going to take the perfect square. Square root of 30, or I'm going to take the square root, excuse me. So square root of 36 is 6. Square root of x to the 4th, remember it's 4 divided by the index. So 4 divided by 2 is 2, so that's x squared. And y squared is 2 divided by 2 is 1, so that's just y. And then I have the square root of 5xy left over. So that is the simplified form of the square root of 180 x to the 5th y to the 3rd. Let's look at this next one. So in this case, 54 is not a perfect cube. So I'm going to break it up into 2 different radical expressions. So when I do that, 54, how can I break 54 up? One factor needs to be a perfect cube. Let's think about some perfect cubes. 1 cubed is 1, doesn't help us much. 2 cubed is 8. 8 will not go into 54. 3 cubed, 3 times 3 is 9 times 3 is 27. 27, that will go into 54. How many times? 2. So I can have the cube root of 27 on this side, and then what's left over? The cube root of 2 on that side. Now let's look at x to the 8th. What is, because x to the 8th is not divisible by 3, but what is the largest number smaller than 8 that is divisible by 3? 6. So I'm going to break this up into x to the 6th and x squared. 6, 7, 8. So 6 plus 2 is 8. Everything looks good. So I'm going to take the cube root of the first part. The cube root of 27 is 3. Let's put this down here. 3. The cube root of x to the 6th is 6 divided by 3 is 2. That's x squared. And then I have the cube root of 2x squared left over. So that is that expression simplified. Let's look at 4 more. So for this first one, I have 12, a to the 4th, b to the 7th, and c to the 3rd, and I want to take the square root of that. 12 is not a perfect square, so I'm going to break this up into 2 square roots. How can we break 12 up into 2 factors, one of which is a perfect square? Well, 1 squared is 1. That doesn't help us much. 2 squared is 4. 4 is a perfect square, and 4 is also a factor of 12. So what times 4 is 12? 3. So I'm going to write 4 in the perfect square part, and I'm going to write 3 in what's left over. Now let's look at the variables. A to the 4th. Well, guess what? 4 is divisible by 2. Excuse me. So I can put a to the 4th over here. That a is a little crazy. Let me erase it. So I can put a to the 4th over here. The whole thing. I don't have to break it up. Okay? Because 4 is divisible by 2. B to the 7th. 7 is not divisible by 2, but I can break it up into b to the 6th on this side and just b on that side, because 6 plus 1 is 7. And c cubed, 3 is not divisible by 2, but I can break this up into c squared and just c. So now what I do next is I look at square root of 4, a to the 4th, b to the 6th, c squared, and I find the actual square root of that. Square root of 4 is 2. The square root of a to the 4th is a squared. Remember, I take 4 and divide it by the index. B to the 3rd, and c. And then what I have left underneath the other radical is the square root of 3bc, and this is the simplified form. Alright, let's take a look at this next one. I'm going to be breaking it up. 147, gee, this one is not as easy. 147, well, I'm here to tell you, I'll make it easier for you. I'm here to tell you that 147 is actually 49 times 3. So 49 is a perfect square. So I write 49 underneath the perfect square part, and then I write 3 in the leftover part. W to the 6th. Well, hey, guess what? W to the 6th. 6 is divisible by 2, so I can write, again, W to the 6th over here. I don't need to break it up. Then I have Q to the 7th. Well, I need to break that up into Q to the 6th and just Q, because 6 and 1 is 7. And then I have R to the 27th. Well, I can break that up into R to the 26th and just R left over, because 26 plus 1 is 27, and 26 is divisible by 2. So I'm going to take the square root of this first radical. Square root of 49, is 7. The square root of W to the 6th is W to the 3rd, because I just divide 6 by 2. The same way with Q to the 6th, I just divide 6 by 2 to get Q to the 3rd. And I divide 26 by 2 to get R raised to the 13th. Right, 26 divided by 2 is 13. And then what I have left over is the square root of 3QR. And that is the simplified form of that radical. Okay, so we dealt with some square roots there. Let's take the 5th root. Now, 32, in fact, is a perfect 5th, but some of these variables may not be. So I'm still going to have a perfect 5th root and a what's left over. But the thing about it is, I don't have to put 32 or break 32 up. I can put 32 all the way over here in the perfect part. Now 10 is divisible by 5, so I can put x to the 10th over here in the perfect part as well. Y to the 6th, though, is not divisible by 5. 6 is not divisible by 5, so I'm going to break this up into y to the 5th and y. Z to the 7th is also, 7 is also not divisible by 5, so I'm going to break this up into z to the 5th and z squared, because 5, 6, 7. 5 plus 2 is 7. Now I take this perfect fifth part, and I just find the fifth root. So the 32, the fifth root of that is 2. Then I have x to the 10th. Well, 10 divided by 5 is 2, so that becomes x squared. 5 divided by 5 is 1, so that becomes just y. And again, 5 divided by 5 is 1, so I just have z left. Then in my what's left over part, I have the fifth root of yz squared. So there we go. Now let's look at this last one. Here I'm dealing with the cube root of 48. That's not a perfect cube, so I'm going to have two expressions. One's going to be a perfect cube part, and the other will be whatever's left over. So 48, how can I break 48 up? Well, what immediately comes to my mind is 6 times 8. 6 times 8 is 48. 8 happens to be a perfect cube, so I'm going to put 8 there, and I'm going to put 6 in the leftover radical expression. Now, x to the third, 3 is divisible by 3, so I can put x to the third in its entirety over here in the perfect cube radical. The same way with y to the ninth. 9 is divisible by 3, so I can put y to the ninth there. I don't have to break it up. But z to the 11th, 11 is not divisible by 3, so I need to have z to the ninth over here and z squared over here. So now I'm going to take the cube root of the perfect cube part. Cube root of 8 is 2. The cube root of x cubed is just x. The cube root of y to the ninth, 9 divided by 3 is 3, so that's y cubed. And z to the ninth, 9 divided by 3 is 3, so that's z cubed. And then I have the cube root of 6z squared left over. And there's not a factor of 6 that is a perfect cube, and 6 itself is not a perfect cube. So I know that this is simplified. Well, I hope that this helps you with your homework this week. Thanks for watching.